Hello and welcome to the Citizen Science Training Modules. I'm Dr. Chuck Higgins from Middle Tennessee State University and the Radio Jove Project. Radio Jove partners with the Sunrise mission to bring you these training modules. Our contributors to these modules are listed below, as well as our funding sources. This is Training Module 1.3, Solar Radio Emissions. This is a list of the prerequisites for this training module, specifically Training Module 1, 1.1, and 1.2. The learning objectives for this module is to understand the radio spectrogram, learn the sources, locations of solar radio waves, see example low frequency solar radio burst, and learn how to identify the 5 different types of solar bursts. First, what is a spectrogram? Well, before that, we define a waveform, which is an amplitude versus time graph of data, most often with sound information. The top graph shows the waveform of 2 seconds of the spoken words sound example. A spectrogram is a visual way of representing the signal strength or loudness of a signal over time at various frequencies present in a particular waveform. One can see where there is higher or lower energy at a particular frequency, and one also sees how energy levels vary over time. Spectrograms are commonly used to display frequency time data. In the example, a frequency versus time versus intensity graph of the spoken words sound example is given in the lower graph. The amplitude of the sounds are given in grayscale, and the louder sounds are depicted as white and quieter sounds in black. A radio spectrogram is typically a 3-dimensional graph of time, frequency, and intensity using a color scale. Shown here is a Radio Jove radio spectrogram of 30 minutes of radio astronomy data over a bandwidth of 16 to 24 megahertz. Time increases from left to right, frequency increases from bottom to top, and the intensity is represented by a rainbow color scale where black is 0 and white is the maximum signal. The near vertical bands of green and yellow represent solar radio bursts of varying intensity. The horizontal bands represent local interference or nearby or distant radio transmissions. The thin slanting signals you see here are radar signals that sweep through the frequency band, sounding out the ionosphere. The Radio Sky spectrogram software is used by Radio Jove from Radio Sky Publishing. This is another example of a radio spectrogram, one from the Colgora Solar Radio Observatory in Australia. They observe the radio emission of the sun from 18 megahertz to 1.8 gigahertz to show how solar flares can radiate energy over a very broad frequency range. Again, frequency increases from bottom to top, the time increases from left to right, and the amplitude is represented by a color palette. This image shows several different types of solar radio bursts. Radio astronomy data is often displayed as a radio strip chart, a 2-dimensional graph of time and intensity at a particular frequency or frequency channel. Shown here is a graph of antenna temperature, which is a measure of the signal strength, versus time. These graphs show 30 minutes of data from a Radio Jove RJ 1.1 receiver at 20.1 megahertz. The bottom graph shows an SDR play radio over 16 to 24 megahertz over the same time period. The graphs are aligned in time to give an example of how solar radio bursts appear in different graphical formats. This is a schematic showing a solar flare region near the sun. A magnetic reconnection loop is shown at the particle acceleration site displayed as the circle. High energy X-rays and microwaves are generated near the solar surface. Upward particle acceleration gives rise to solar radio bursts with lower frequency emissions generated farther out in the corona. The 15 to 30 megahertz emissions come from regions about 1 to 2 solar radii above the photosphere. During solar activity, the sun effectively converts magnetic energy into kinetic energy of accelerated particles in solar flares. Understanding electron propagation and acceleration is one of the key elements of the Sun-Earth connection studies, and as such, an important element of space weather. This figure shows the sun imaged at multiple radio frequencies. The higher frequency, higher energy radio emissions shown in the upper left occur near regions of intense magnetic activity close to the sun's surface. At lower frequencies, the radio source regions occur farther out in the corona where the plasma and magnetic fields are disturbed by solar flares or coronal mass ejection events. The solid line represents the size of the sun in the image in visible light, and the dashed lines show the regions where the radio emissions are generated at the frequency indicated. Again, for radio, Jove, and/or sunrise frequencies of interest, 15 to 30 megahertz, the figure in the lower right is the most relevant. This is a brief description of the 5 types of solar radio burst from Montana State University. I won't read all of this information, but each type has a characteristic signature in a spectrogram. Now, the type 3 is the most common observed radio burst, with type 2, 4, and 5 being much less common. Now, to be clear, type 1 solar radio events are common, but they are not observed down below 50 or 40 megahertz. More details on the various types and their characteristics can be found from Professor Dale Gary's website at the New Jersey Institute of Technology, a really great resource. This is an overview of the different types of solar radio bursts associated with a solar flare. Not all components are emitted or observed, as the emission mechanisms are highly variable. Because the HF band is below 30 megahertz, not all types are seen, as I mentioned before. Type 3s, again, are very common. Type 2, 4, and 5 are not as common. And type 1 events, as you see in the spectrogram here, those typically don't go down below about 50 megahertz. Here's some examples of solar radio bursts from the Nancy decameter array in France. A type 3 is seen on graph A over here, and on graph B this is a type 2, and then on graph C is a type 4 event. Notice the frequency extent of these emissions as well as the time scale of each. Again, type 1's events are not observed at frequencies below about 40 megahertz, but to be complete, I show you a couple of images of type 1 solar bursts here. They typically occur in storms and consist of thousands of short duration and narrow bandwidth bursts, and they're often accompanied by an underlying continuum. You see the figure, the lower figure here shows type 1 also containing drifting chains. This spectrogram shows 2 type 2s and 2 type 3 solar radio bursts. These events are much stronger than the background reference from an electrical storm. Notice that the type 2s are slowly drifting in frequency and time. In addition to the fundamental and harmonic structure, these type 2 events clearly exhibit band splitting. This is where the components of a type 2 fundamental and or harmonic are themselves split into 2 or more roughly parallel bands. Very often type 2s are preceded by type 3 activity. This is an example of a type 2 solar radio burst. The strip chart at 20.1 megahertz was captured at Windward Community College on the island Oahu in Hawaii on July 28, 2000, using an original Radio Jove receiver and a standard dual dipole antenna. The second image shows a superposition of the 20.1 megahertz strip chart on to an 18 to 100 megahertz spectrograph taken at the Kougara Radio Observatory in Australia. The images are time aligned, and it's easy to see the correspondence in many major and some minor aspects of the bursts. This shows multiple type 3 solar radio bursts on the spectrogram in the upper right, and this is from John Cox in June 2023 from his observatory in South Carolina. Notice that the type 3 bursts are called fast radio drift bursts. They drift very rapidly in frequency. The graph below is taken at 2 frequencies and shows strip charts of a type 3 solar burst, and it shows the classic shark fin shape on an intensity time strip chart. The red and blue are recorded at 2 different frequencies. This is an example of type 3 solar bursts from a 16 to 24 megahertz radio spectrograph from October 2021 from myself at our dairy farm in Murfreesboro, Tennessee. This is an example type 4 solar burst from the Nancy decameter array in France. Again, these are broadband features and slowly drifting in time over many tens of minutes. This shows type 3 and type 4 solar bursts from June 2023 from Tom Ashcraft in New Mexico. The type 3s are associated with an X-class solar flare, and we think this is a moving type 4 solar emission caused by post-flare plasma disturbances. Also notice the blackout regions after the type 3 solar flares. This is common where you get radio emission blackouts after a large energetic event. And lastly, we have type 5 events. They are always preceded by 1 or more type 3 bursts of at least moderate intensity, as seen in the figure. The spectrogram is typical in that a type 5 begins at the same time as the type 3, but they tend to persist longer at mid to low frequencies, and also typical is the less protracted duration at the lowest observable frequencies. You can see the sort of the rounded shape at the lowest frequencies. This is a complex spectrogram showing a type 3 here, and you see a type 5 as well, with 1 or 2 type 2 solar bursts, slowly drifting type 2s. Here's a list of great resources for solar radio astronomy, so I encourage you to check out some of those. Again, thank you for watching, and next we will examine Jupiter low frequency radio emissions.